All right, I just started recording. Hopefully audio is okay. Um, I can like try to talk louder this whole time. I know it's not really working through my normal system, so I instead have to do it through my actual laptop, which hasn't had to happen before. But you know what? We are just trying to work with what times we are in. I do have the same setup rather than on the whiteboard, which is cool. I don't know if you guys can see me. I'm gonna be like sort of like gesturing around. Hello, how's it going?
Hi, good. How are you?
Glad to hear it. Glad to hear. I like just started recording. We're sort of like getting into an intro thing. But now that you're here, I guess I can just like get right into this stuff. Um, I was going today. I was going to go over what we did basically on Friday. So like pretty recent things. Basically talking about like derivatives and like the shape of graphs and how like one function. So if you have like one function, how does it relate to? How does a graph of it relate to like the derivative functions graph and then like the second order derivatives graph, that kind of thing? Is that sort of like a good idea, sort of something that you'd be interested in going over with me? Stuff like that. I can't really hear you.
Can you hear me now?
Yeah, that's better.
I actually had a question on the web. Yeah, it was like a couple questions on the WebAssign that I just like didn't really know how to do.
Okay. Do you want to like share your screen and then I can just sort of take a look at them?
Sure. Yeah. Yeah. Let me just pull it up really quick.
Fine. Cool. Okay. Yeah. Feel free to share like whenever.
Okay. Yeah. It's just loading.
Cool. What topic is it over?
Um, it's 3.4. Wait a sec. Let me just share my screen.
Oh, 3.4.
Yeah.
So derivatives as rates of change. Okay.
Yeah, it was just like part B I didn't really like know how to do.
Mm-hmm. Yeah.
So
No, for sure, for sure. Okay. So, um, I wish I could like. Okay, hold on. I wish I could sort of write this question down because it's actually a good. It's actually a good question. Um. Okay. For t equals 0. Let me like write it down really quickly.
mm,
T cubed minus 3t squared plus 8. T is greater than or equal to 0. That's s of t. Okay. So we want to find velocity. Okay. Find v of t, a of t, and then also when is og speeding up, slow down speeding up. Okay, cool. Okay, can I share my screen again so you can just like remove yours and I can just do mine, or I think I can just like override. Oh wait, no, I can't. Okay, cool, now I can do it. Okay, so here's my poorly drawn out thing. I have awful handwriting, but you know what? I think the numbers are still pretty clear. So the main idea that we're trying to like get around to sort of like think about for this kind of problem is the how do like position, velocity, and acceleration relate to like one function and then its first and second order derivatives, right? So one thing that we might know about position and its sort of relationship with regards to velocity and acceleration is that if we start sort of with like the we can say this is yeah. So if we say like s of t is like something, it's like arbitrary, then we know that v of t is the derivative of that s of t function, right? Because this is position, this is vel, and then if we say a of t, That's the derivative of that. Sorry, again, awful handwriting. The derivative of that velocity function, right? Okay. So it's xl, which is also equal to the double derivative of s of t, right? Can you see this okay? Is this like the picture is okay? Okay, fantastic.
Yeah, it's good.
Cool. So if I remember correctly, you did find v of t and a of t well and everything, which 6t. Is that it? And then is that right? Cool. Okay, so these are great. So the first thing to sort of like think about when we're dealing with these is that, okay, so it actually kind of does relate to sort of like shape of graphs and like what, like, okay, the original function is like doing some like like a polynomial thing, and what does its derivative look like? So the first thing to sort of think about with regards to how position and velocity are first related is that velocity is basically a measure of the slope of the position graph. Does that sort of like make sense at all? So if you, for example, had something like s of t going like this, so therefore you're like going like this. This is s of t. I guess there wouldn't be a thing. And then it's like this, and then that. How's it going? So if you had s of t kind of looking, wait, you can't see what I'm doing on here. Oh man, okay, wait. Let me get this display on.
I can figure it out if it's speaking it out.
I think we can be okay, but I'm not sure.
All right, we'll see.
The projector needs to turn on. This is kind of stressful now. Sorry, someone's like here in person, and I don't know how to deal with this. Okay. That is not turned on, is it?
It's all right.
Oh, I think it's like beeping. I'm not sure. Maybe you can, I mean, you have your laptop, right? So you can just look at that. That would be helpful. We'll figure that out another time. No, you're totally good. You're totally good. Thanks for coming. Okay, so we have like s of t kind of looking like this. We can tell that, okay, this is position, right? So as time goes on in that direction, this is sort of just like moving at a constant velocity here, right? Because we're just like sort of literally just like if we're like walking, for example, we're just like walking in a straight line, not moving at all. And then once we get here, our position isn't changing at all, right? It's just kind of stopped for a little moment. And then we start walking backwards. But we're still like going, but I mean, yeah, we start going backwards, right? Does that make sense? Or in the negative direction, right? So when we have something that's sort of like this though, this is a little bit different, right? Because instead of, a constant change of position, now we have that variable change of position where, okay, now we're like kind of speeding up a little bit. And now we're kind of like slowing down, right? Does that sort of make sense? So the big thing to sort of note is that something that I've sort of drawn right here when in my notes. I'm too lazy to like draw these things out. Oh wait, okay, fantastic. Is that so? Say this is like your original function. Say this is your s of t function, right? Right here, you can see that this slope, it's sort of in red. I don't know if you can like see that too well. Okay, it's like sort of in red. That slope is going up, right? So because that is going up, that slope is positive. Therefore, the derivative of this function from like, like from this point up until 2, for example, it's going to be like the entire like function, that derivative function, those values are going to be positive. So what that might look like is something like this. So this is 2. It might look something like this, right? Because it's going to be positive, but it's getting less, and the slope is getting less and less positive, right? So say this is like a 1 slope. Okay, say this is like 1, like here or something. I don't know. And then eventually it gets to 0, which is right where that slope with 0 happens. Does that make sense? Cool. So when we're talking specifically about like speeding up and slowing down and what that sort of means, when we're talking about speeding up, something speeding up, that's specifically referring to acceleration. Because when we're talking about speeding up, that means we're getting faster and faster and faster over time, right? versus slowing down, our overall speed or velocity is getting slower. Okay, so when we talk
It's like,
yeah.
do you want me to look at the graph of the acceleration for questions like that?
So you could actually look at position or velocity or velocity graphs or the acceleration graph for that. Right? Because if we look at the position graph, wherever there's a time when it's like sort of like curving upward or with that positive concavity, right? So when we sort of have something that's like when we sort of have something like this, that's like curved up. And so a point like from here to here on like, I don't know, like that would be something when it's speeding up. And it's easier to find this for some arbitrary function that we have up here when you do this derivative stuff, right? Or if we're looking at the velocity graph, it'll just be whenever like the slope is sort of just like consistently going upward, because that means that the velocity is changing over time, right? Because like velocity is this. So like if this is like 1 and this is 2, then between this time period of A and this time period of B, our velocity increased from 1 to 2, which meant that we were speeding up over that time period as well, right? Does that make sense? So if this slope throughout this point is like 1 or something, like the slope of it, that means that, so this is V of t, it's S of t. Then our A of t, sorry, this is getting really bad, would just be like 1. This is like 1 on like this, right? Does that make sense? Because it's like a constant velocity, like constant, constant acceleration. We're getting faster over time, but at a constant rate, right? So if we're trying to find the time periods from when, we're speeding up and slowing down, we want to find those time periods where our velocity is increasing or when our acceleration is decreasing, right? Huh?
Will acceleration ever not be a constant?
So the acceleration doesn't have to be a constant. I mean, in this example that we have right here, it's changing, it's variable. So like the equation of this, I mean, is something like it's something like this, right? It like has like, if this is like a negative, sorry, this is like -6 where it like crosses the y-intercept, and it has like a slope of 12. So acceleration doesn't have to be constant. If you take like, but it's just, that's sort of normally how far we go. I think in like later physics classes, you'll learn about like jerk, which is like the derivative of acceleration, and it's kind of like, okay, how does acceleration change over time? But that's not like as like looked into sort of. So the things you want to really know about is like, okay, when is acceleration positive, right? Or when is velocity negative? Acceleration negative, when we're talking about specifically slowing down and speeding up. Does that sort of make sense? Because like, again, if this is we already established that this is like speeding up, right? So if we're talking about like something like this is slowing down. This has a positive slope. This has a negative slope. The derivative of velocity is acceleration, right? As we can see right here. So if we have a positive slope for when we're increasing, and we have when we're speeding up, and we have a negative slope for when we're decreasing, then we can tell, okay, are we what's the word? Okay, so we can tell, okay, if we're increasing here, obviously we're like gonna be positive, or right here we're gonna be negative. Sorry, that like literally made sense. I like lost my train of thought.
I think that it was slowing down when the signs were.
Yeah. So I was about to get to that. Yeah. So this is sort of like telling about sort of like, okay, like this can be positive, right? And then like, so if we're like increasing our slope when we're also positive in the velocity, then we can tell, oh, okay, we're like getting faster and going into that same direction. Whereas when we're talking about like this kind of thing, we are we're still like moving in that one direction. How do I say this? I feel like there's some point in my notes somewhere that I had like a way better example for how this sort of like all went up. This is like what, 3.4, right? This is way back. Oh wait, here it is. I found it. Okay, yeah. So I have it right here in my notes. So I probably should have just like started with this. But it's kind of like the best way to think about it. So yeah, I mean, this is just very explicitly sort of stating like the different rules. So an object is moving forward when its velocity is positive. So that means that like it is act at any point if the velocity is, if the graph of like some object's movement, if its velocity is positive at any point, then we know that it is actively moving in the forward direction. Okay. Versus if its velocity is negative, then we know that it's moving in that negative direction at that specific time, right?
Does it like have anything to do with like when it's below like the y, like the x-axis or something?
Yeah. So that's what this part right here sort of talks about. So if our object has the same velocity and acceleration sign, therefore we know that not only is it moving in one direction, but it's also speeding up in that same direction, right? So if I'm like sort of, I guess you can like sort of see my whiteboard, right? It might be easier to like draw on here. Let me get my marker real quick. Sorry. Actually, no, it's literally just easier if I write this down on here. Okay. So if I'm like going along, I say this is like the positive direction, like positive, and this is like negative. So if I'm like going along like this, at like a constant speed, right? I'm moving in that positive direction. But if I'm like going along, oh shoot. Okay, this is bad. Okay. If I'm going to like go slowly and then sort of like keep getting faster and faster and keep going over, that's when we're like sort of speeding up because the acceleration is pointing in that same direction over that way, right? Versus, I could be moving in this positive direction, but I could start out really fast, but then I could start out really fast, but over time, like get slower and slower and slower, right? So that's an instance of where, okay, we have that positive velocity because we're still moving in that right direction, but we're slowing down because the acceleration is pointing to the left. Right? So when we need to find, okay, are we accelerating or are we speeding up or slowing down? We not only need to find out what the when the velocity graph is both positive and negative, but we also need to find out when the acceleration graph is positive and negative, and then we need to compare the two at the same time. Yeah. So okay, that was a lot of like concepts and not much like math that we can just like do, right? So how do you think we should sort of just like take these velocity and acceleration functions that we found right here and then turn that into something that we can use to compare to each other? You can also answer.
You like set it, if you like set them equal to 0, you could find the y-intercepts, I guess, so then you would know like when it goes like below the
Yeah.
x-axis.
Yeah, so we want to find the points of the moments of t where each of these graphs equals 0, right? So it's more like finding the x-intercepts rather than the y-intercepts, right? Because that's when, we have some function and then it like, hits there, right? We're finding this. Okay, cool. So is it minus 6t?
Because when velocity is 0, the graph is just going.
If the velocity, what'd you say?
Velocity is 0.
Yeah. So if the velocity is 0, then the position graph is just like the straight flat line because the position graph's flat line like a slope of 0, therefore the velocity, yeah. For sure. Okay, and then what is AFT? It's just 12t minus 6, right? Okay, so let's try solving for v of t first. Let's try solving v of t first, right? So we're gonna set 0 equal to this. So how would I sort of like continue on?
can factor out a 6
Okay.
as like the GCF.
Yeah. What is that like? Is that like no, it's not. It's 12. Yeah, I'm just dumb. Okay. Cool. Now what?
And then the first would be like 3 and negative 4.
You think it's 3, negative 4?
So it would be like t plus 3 and then t minus 4. Yeah.
Yeah. So do you see how we factored that? Yeah. Cool, cool. Because that's like negative 12 and then plus 3 minus 4. Yeah, t squared. Cool. And then we can just like set these each equal to being to 0, right? Okay, and then 0 equals t. Then negative 3 equals t. Okay, cool. So we have these two parts. Only one of them is valid though. And I know you don't like see this rule on that other page, so I'm just going to tell you. We're only looking at where t is greater than or equal to 0, right? We can't really have negative t. So whenever we're dealing with like velocity and like position and acceleration, we only want to look at these values of t when it's positive. So you cross that out, right? Okay. So now that we have a point for this, oh, this is actually interesting. Now that we have a point here where our velocity hits 0, we can we need to now use a table of values to find out where, how should I say this? You need to use a table of values to find out like, okay, which side of this point, like t equals 4, is it positive? And then which part is it negative? Because right now we could be like, okay, take this as 4. It could be like this, right? So over here is positive, over here is negative. Or it could be like 4 like here, whereas this is negative, right? And that's positive. Does that make sense? Cool. So we need that table of values, right? So you just do how do you even like make one of these again? Right? Okay, I get it now. Sorry. all right. So do you know how to like draw these out, or do you just want me to like sort of? Yeah. So it's kind of like this, and then you have like 4, and you have like your what is it, like t minus 4, right? So then you basically take a value from over here somewhere, and then also over here, and plug it in for this and see if it's positive or negative, right? So we could say for like t minus 4, looking at here, okay, so if we plug in a value like 2 or something, 2 minus 4 is negative 2, so that's negative, right? We can plug in a value like, what? No, yeah, I mean, it's like the same thing because if you take this for example, if you plug in 2, this is gonna be positive, right? Like 2 plus 3, and then this is gonna be negative. That's gonna make the whole thing negative. Yeah. So you only have to worry about each individual 0. Or if this was like, okay, so if this was like a minus 3 instead, you could do like a this. And then you have to do it for both. So if you did a 2, plug 2 in. Yeah, but you'd also have to mark down both 0 points. So you'd also have to mark down like a 3 and then do the part in between, stuff like that. But we don't have to worry about that right now. So yeah, it's only about like the individual zeros. Okay, so we plug in 5, we get that that's like positive, right? Because 5 minus 4 is 1. Cool. And if I like graphed it out and showed you what this looks like, you would see this as well. So everything to the right of 4 is positive, and everything to the left, at least until like t equals 0, is negative. And so what that means is that it's more like this one and not this, right? You sort of see that? So like right here, that velocity, like the values of the velocity function to the left of 4 are negative, and the values to the right of 4 of the velocity function are positive. Okay, cool. So we got that. Now we need to do it for acceleration as well. So, I mean, that's a lot simpler to sort of solve for t, right? I literally can't write anything. T minus 6. So what do you do? This, then you get 1/2. Okay, cool. And then what do we do? Honestly, like, okay, wait, so
You have to like match them up. So
yeah, 1/2, right? I mean,
don't you want to match them up? Like,
what'd you
I
say?
guess this matched up now. Never mind.
Oh, yeah. So I was gonna do it like here, and then we're just gonna like
Yeah.
plug it in again. Yeah. So now we kind of want to find out where the acceleration is, right? So what? So if we can plug in like 12, I guess we can just do like 12t minus 6. So you want to plug in like values less than 0, I mean less than 1/2, and then also values greater than 1/2 in, right? So we can do like 1. So 12 times 1 is 12 minus 6, that's positive. Then on here, if we plug in like something like 0.25, 12 times 0.25 or 1/4, 12 times that is just 3, right? And then minus 6, that's negative. Yeah. That makes sense. Okay, cool. So now that we have these two, we actually need to combine them. Because remember from earlier, we need to see if the velocity and acceleration graphs have the same sign, right? So we need to tell when that is. So not only do we need to combine these, how do I say this? We need to both combine them, and we need to find a couple more like specific locations for like, okay, is it positive, negative, that kind of thing. To then and then we can like compare the each sign alongside along the top of the number line, sort of, to then tell, oh, okay, this is when it's increasing. This is when like the velocity is positive. This one the acceleration is positive. Therefore, it's speeding up, that kind of thing. So to sort of like
Is it
really,
just slowing down between 1/2 and 4?
what?
Is it not just slowing down between 1/2 and 4 and then speeding up everywhere else?
I mean like,
Or is there
yeah. Well, you see, okay, so I'll show you. It'll be because you got to see like on the other side of 1/2 over here, it's also negative, so it's also speeding up on the left.
that's what I was saying.
Yeah, and then there's like a middle
Only
part,
between up here
and then on the
and
right.
stuff.
Yeah. So I'll just like show this. Cool. So here's 4, 1/2, and then we're trying to solve this for these two things, right? Because these are what's important. So I'll do like t minus 4. This is like b of t. This is like a of t. So this is 12t minus 6. Cool. So now we just need to plug in values in between each of these specific things in addition to sort of what we've done up here, right? So we already know what this one is for t minus 4, right? What the value is greater than 4 for t minus 4, right? It's going to be positive. Does that make sense? So positive. Okay. And we know what they're going to be less than this, right? Well, yeah, we already know what it is, right? So we know what all the values over here are negative for less than 4, right? So we can also just say boom, negative. Okay. And you can basically just do the same thing for what we've done, what we have for the 12t minus 6 in the 1/2. So anything anything to the left of 1/2 is negative. Okay. Anything to the right is positive. Cool.
I have chapter now, so I'm just gonna like watch the recording later.
Okay, sounds good. As you
Alright.
can, okay, good. If you have to go, then I understand.
Okay, yeah. It's like starting like right now. So
Yeah, you're good. It'll be posted.
thank you.
Yeah.
Bye.
Okay, I take way too long in these. All right. So I mean, as you can see, this is like speeding up, but in like the negative direction, right?
Yeah.
So I guess I have to like finish the problem out. So this interval speeding up. This is slowing down. Well, actually, it's no, it is slowing down. V of t is in the negative direction, slowing down. V of t.
At 1/2 and 4, the velocity is 0.
Yes, that's what we found right here, right? So if you plug in like t equals 4 here, then for the velocity function, you're going to get a value of 0. So that's why we have like that x-intercept, right?
And for 1/2.
For 1/2, that's where the acceleration is going to be at 0. So that's where like, so if you plug this in, I mean, as I said before, 12t minus 6 is something like, it's going to look something like this, right? So this would be 1/2. This would be -6, right? So like everything to the left of 1/2 is negative right there. Everything to the right is positive. Yeah, cool. And then right here we have speeding up. B of t positive. Awesome. So if I were to sort of like draw a little bit of a graph, I guess, of what this would look like, say like over here is our positive direction, over here is our negative direction. It would sort of start somewhere over here. It would be like going really fast over in this direction until 1/2, and then it starts slowing down a little bit. And then right when we hit 4, not only that's when our direction changes, right? We start going in that positive direction. So then at like t equals 4, well, how should I say this? Okay, so if this is like t equals 4, sorry, like doing these things are like so hard to draw out. So this is like 1/2. Say we're accelerating, we start accelerating like right here, like boom, and then we're accelerating in the negative direction. We hit 1/2, and we're still moving in that negative direction, but we're getting slower and slower because that's when our acceleration changes right here, right? And so from then on out, the object wants to go in this direction, but it still has that initial sort of like velocity to the left. So it's got to take some time to sort of then turn right around at 4. And then from then on out, it sort of just accelerates all the way into like infinity. Yeah. Cool.
Can you explain linear approximation?
Yeah.
I do not.
Yeah, I can go over that. I did have a session on that. I posted it. I think like let me see. And I can go over it again for sure. But I think I did do that, and you can like check it out again. I do remember that was a good session as well. So I think that was like not bad, but I can definitely go over that again. Actually, no, I don't think it was. I think it did pretty poorly. But it's whatever. I think I remember I wanted to say one more thing about this. I forget what it was. Shoot. Yeah, I mean, it's fine. This sort of like is a good showing of how it all sort of like lays out. So yeah, just understanding like the differences between like velocity, acceleration, what like going in the positive direction versus like accelerating in the positive direction, the differences between that, and then like accelerating or moving in the negative direction and how those all sort of like intertwine. Very, very important. Okay. So yeah, we can go into a bit of linear approximation. I'm probably just gonna, I don't have any other examples other than like the one I already went over, but I think it's a good example. Oh, okay. Yeah, we can, I mean, if you wanna like sort of like tell me something.
So determine the appropriate f of x and a, and evaluate L of x equals f of a plus f prime of a parentheses x minus a.
Yeah. So what's like the f of x?
It's it says 0.99 to the 30.
Oh,
It
okay.
doesn't say f of x.
Oh, okay. So I want to eval. What is it? Like this. Okay, cool. Awesome. So what linear approximation, the sort of idea of it is, honestly, like it's better if I just like show you what I drew back then, because I was looking at someone else do it. Oh wait, it's different time. I'm so dumb. Okay. So this is actually no. this is sort of a better way to sort of like show what it is like right here. I like this graph a lot. So say this square root graph is instead like the cubic graph, the cubic function, right? Which instead of doing like this kind of thing, it would sort of go up like that, right? But it's sort of the similar idea. So right here in this example, we were trying to estimate 8.1, but through on like which is right here, but using the tangent line to this function, the cube root of x, at 8 instead, because we know what the cube root of 8 is, right? So basically the whole idea behind linear approximation is, okay, I want to evaluate some kind of expression. Let me find some function to model all of that after, right? I mean, a model like, how should I say? When we're doing some kind of like some kind of expression, it's using a function that we can sort of like generalize it with. So when we're looking at this 0.99 to the third, we can say that goes to f of x equals x cubed, right? Because what we're doing is you're using this x cubed function, but just plugging 0.99 into it, right? Okay. So we don't know what 0.99 cubed is. I mean, we could find it if you wanted to do the whole like 99. Sorry,
That
I'm
was
like,
the first, that was the first part, and I think I was asked to calculate the numerical error in the linear approximation.
yeah. So like we could do this, but we would only have a fraction, and we don't want to like we don't know what the decimal is, right? So this is like a bad way to do it. So instead, we find an x value to plug into this that is very close to what we already have, but not the same, but something that we can also like find and that we know that we can like, solve this expression for, in a sense. So in this case, like 0.99, very close to 1, right? Like super close to 1. And we know what 1 cubed is, right? 1 cubed is 1. So in this case, a would be our 1 would be our a value, because we're using that like, I'll show you this. Trying to think. Like I know what I know what's like I know what I'm trying to get across. I just don't know how to like say it. Okay. Can I sort of like take you through the work that I have in this example, and then we can try to like apply it to the other one? Okay. So in this case, we want to use a linear approximation to estimate 8.1, the cube root of 8.1 of 8.1, right? So we recognize that like this cube root is a cube root function, right? So we can say that f of x equals the cube root of x. And we choose this a of 8 value because we want a value of a that is a this is the number that we know the value that we can like evaluate for this function, right? Like we can plug in 8 and get out 2 of it. We know that. We don't know 8.1 though, right? And we want it to be close to x. So those are sort of like the two conditions for choosing an a value. It's like 1, it should be close to that original x value, which in this case is 8.1. In this case, it's 0.99, right? Because like if you knew f of 0.99, you get like 0.99 cubed, right? That's how it works. So again, we want a number that's close to x, and we want something that, an a value that we can plug into that f of x function and get something out of it without having to like use a calculator or anything, right? So the idea is for that sort of a value, we want to find the tangent line of the function at that a value. So in this case, we find the tangent line to the function, the cube root of x, but at 8 instead of 8.1. And then we basically plug in 8.1 for that and then get something that's super, super close, right? So in this case, we found this tangent line function, or this tangent line to this cube root function. Then we just plugged in 8.1. and then got whatever this is instead of getting whatever this is. And it ends up being pretty close. And they always use this like L of X thing right here. Or it's instead put like right here. So like we've always used this L of X thing right here. We get this directly from the point slope formula, right? Or I mean, not the point slope formula. Oh my God, the slope intercept. I know it is straight up is point slope. My bad. So so looking at this, which of these points corresponds to that normal point slope formula that we know, which is like what, y minus y1 equals mx minus x1, right? So how should I say this? We're trying to find an approximation for f of x, right? F of x being, you know, cube root of 8.1, like 0.99 cubes. So that's sort of what we're trying to find. So that's basically corresponds to like the point that we plug in, which is y. And then whatever x value that we have, that's x, right? Which corresponds to this x value here and this f of x value here, right? Because if we take some function, plug x in, then eventually we get f of x out, right? Okay. So then we use this whole like idea of using a and f of a. That's where that's where these two numbers come in, right? So we also have this value of a, which, you know, in my example is 8, in your example would be 1. We basically plug those values in. So we plug in 1 here, if we're trying to use your example, or we plug in f of 1 here, which would also be 1. And we also find the derivative of that function that we're trying to use to sort of model this this whole approximation thing for. And we plug in our and we find the value of the slope at that a value as well. So like I can sort of point out all the different parts that we're trying to find and this point right here. So if we're trying to find this specific point on the function f of x, where f of x equals cube root of x, what should I say? We're trying to find this specific point. So to approximate that, we use this tangent line. We use the slope of this tangent line from this a value. So we use this a value, right? We use the a value, which is which you can see right here in the formula. We use the output of the a value when we use the a value as an input, right? So how should I say this? I guess I could just like take you through. We use the output of that a value, which we can see as being right here, f of a. And we also use the slope of the function of the tangent line that we already used. And then also we know what the input is that we're trying to like approximate. It's just we're always solving for this idea of f of x, which when you plug in a constant for it is just some number. And that's what we're trying to sort of like guesstimate or approximate, right? So if I sort of take you through this whole like problem really quickly, we choose some kind of like a value. It's basically like almost like a recipe of how you solve these kinds of problems. So when you first are like shown like, hey, approximate this, the first two things you should find again are like, I need an a value, I need an f of x, right? The second step you need to do is you need to find the equation for the tangent line at that a value. Because that's sort of like what we were sort of doing right here, right? Is we were finding the equation for that tangent line. And so like pretty easily, we can take the derivative of that function, right? So we take, how should I say? We take the derivative of that original function, and then plug that value of a in, and then we get the slope of that point. So as you can see, like sort of here, we want to find an equation for this tangent line to this point to this function at this point, x equals 8. And we know that we have a point like right here, which is like 8, and then it goes up 2 from just plugging it in. And then to find the slope, we just need to plug 8 in, and then we get something from it, right? So that's what we do right here. Get the f prime of 8, and then sort of follow it over to get this like slope of 12, which is basically the slope of this tangent line. And then from there, originally we kind of just plugged it into point slope form at this point. And then all we were trying to do is just solve for y based upon sort of like these things. Yeah. Okay. Maybe it's better if I just sort of like go through it. Okay. So first steps, let me just like zoom out a little bit. First steps, find f of x a, which we already did, right? Okay, cool. The second thing we need the slope of tangent line at f of a. So how do we get that? We need f prime of a, right? And from there, we can basically just plug in and solve for stuff. So this is just like another one of the ways that you can sort of like use derivatives to sort of, it's like, again, it's like an application of derivatives. It's just, okay, it's sort of follows that same methodology of like, okay, I just like find the derivative of this function, plug in some value, get the slope of it from something, and then we're sort of like chilling. So we need this f prime of a. And then I guess we also need like the point like a, f of a. That's not like as important right now. Okay. So for this function, we need to find f prime of x, right? To then plug a into it later. So if f of x is x cubed, what's f prime of x? Yeah. Okay. So then we need to find f prime of a. So that's a 3, I guess. We're choosing 1. Weird. Equals just 3, right? So that's our n. That's our slope. That's what we found right here. Okay, good. And then 3, it's basically just plug stuff in. So what do we have? We have L of x equals f of a plus f prime of a. And then times x minus a. We already have values for literally all of these things, right? So what are they? F of a is, f of a is 1. Because f of a is just 1 cubed equals 1. Cool. Okay, what's f prime of a? 3. Cool. Okay, what's our x? That's originally what we're starting with, and that's what we're trying to find. Okay, then what's our a? 1. Cool. And this is L of x. Or it's about f of x, which is, again, 0.99. Or 0.99, it's about 0.9, right?
Yeah. So I got 1.03.
Or what is it? 0.99 cubed, right? Okay. So you got 1 plus 3 times 0.01 equals what? 1.03, yeah. Okay. And so if I quickly do this on my calculator,
So wouldn't it be 0.06 if you did numerical error in linear approximation?
yeah.
rounded to 5 decimals.
Is that what they're sort of like looking for you to do?
Yeah, I
Just
think
to round it
that's-
properly?
That's really helpful, actually. I didn't know how to get through those steps before.
Oh, wait, hold on. That's. Oh, wait, so hold on. Okay, just a second. I thought something was wrong. Okay. So this is a negative 0.01, right? Okay. And so 1 minus, yeah, so it's negative 0.97, right?
Uh-huh.
Does that make more sense?
But, yeah.
And that's why I was confused when I did the whole 0.99 times 0.99 times 0.99 thing. I was expecting to get something more like this and not 1.03. This is not negative, this is positive.
Uh-huh. Okay.
Does that make more sense?
So it's much closer to the actual.
Yeah.
Okay.
Sorry, I just
And that's
I
all.
just did not take this negative into consideration. My bad. So those are sort of the steps. Again, it's really basically just like doing some basic derivative finding and plugging in the right values. I know my explanation for why you do that was awful, but again, I can sort of like hash that out later, or you can just go to his office hours. Like he'll be able to explain it way better than me.
No, that helped a lot. Okay, that makes sense. I just didn't know how to like go through this stuff.
Yeah. Oh, okay, so like I mean that's like a big thing that I realized after how should I say? After taking this course is that like pretty much every single like word problem that you're gonna do seems really daunting when you're first learning them, but every single one that you do is basically the exact same, at least with regards to like within a scope of each type of problem, of like word problem, like something like this. They have the exact same like methodology and set of instructions or recipe they can basically just follow, and eventually you'll get the right answer. So when we start doing related rates soon, that's also something that's like a little bit more complex, but um, basically as how I learned it was just like, okay, like you just need to know all the different steps, and whereas different shapes that we're sort of doing stuff with might change how we find like the perimeter or the area. It's basically all following the exact same sort of stepwise process to eventually get that final answer. And it's the exact same thing with linear approximation. What did I do last time? It's the exact same thing, especially with absolute maximum minimum. I think I went over that pretty well last session. So if you're sort of having trouble finding those kinds of things, definitely recommend looking into that.
So is change in Y just LX?
What do you mean? So the change in so like the like dy is L of x. Is that what you're asking?
It's asking me to like how accurate is DY in approximating?
Oh, okay. So that sort of gets into like,
Is that different?
okay. Yeah. So I can explain. So I can so that sort of gets into explaining why all of this like linear approximation stuff sort of works in the first place. This graph sort of has everything on it that you need. I don't know if you can like see all this very well. So right here we have our A value that we're using to approximate things, right? So that's our 1, that's our 8 to our X, which is our 0.99, 8.1, right? So this is actually this is like gray right here. You can't see it. But this X value, depending on if you plug it into the actual f of X or into our L of X, it has a different value, right? The difference between those values is that d of y. Yes. Okay. I'm sorry. I just need to like sort of sort of think. Okay. Does that make sense? Yeah. So. Oh, okay. Wait. Let me retrace my steps. So do you understand why like this, okay, this is f of x, and then this is L of x. Do you understand what L of x represents, right? It's like this, it's the tangent line, right? So we use that tangent line and plug different stuff in, and then we can tell that there's like a difference between what we get from the tangent line versus what we get from the actual function, right? Because, I mean, I don't know if you like sort of seen the whole thing where like, if you take some graph and you zoom really, really, really far into it, even though it might be curvy, eventually it'll look like a line. And that idea is what we're sort of trying to like use with this, all this linear approximation stuff. Yeah. So if we have some like curve thing, woo, I can just be like, oh, like that's kind of close, right? I know this is like poorly drawn, but like that's what it's sort of it's like trying to do. Like here and here, like that's pretty close. And if you zoom in like really, really close into it, it'd be like, you know, straight. So something like that. So when we think about like delta y, that's specifically the difference in how should I say this? It's like the slope formula, right? In the outputs, depending on two different x inputs, right? So if we have sort of again, like delta x equals like, I don't know, like b minus a, then delta y equals f of b minus f of a, right?
So when it's saying like calculate dy for this value from x and dx is just
dx and dy are so
that far off of the actual x value.
So right here, I don't know if you can like see this very well.
Yeah.
Dx and delta x are actually the exact same thing, because we base our.
So it's just a point it's giving you how far off from the x value the point is.
Yeah, exactly. So we have like a. That's the difference between the a and x, right? Okay. So delta y is the difference between when you plug in a. So f of a and f of x, right? Okay, cool.
It's the horizontal difference.
Yeah. Or it's delta y is more the vertical, right?
Yeah.
Because as you can see, because as you can see here, we plug in a, right? And we get this point on gray, on the gray. Plug in x for f of x, and we get this point as gray, right? Okay. But then if we use only L of x, that's where the dy comes in play. So if we plug in a into L of x, we get the same value here, right? As what we did when we plugged in a for f of x, right? Because it's the tangent line to that function, which means that it only hits it right there, right? So if we say like L of a equals f of a, right? Right here. So we have L of x, right, which is blue, then f of x, which is in gray.
Yeah.
We plug in a
Yeah.
for f of x.
Oh, and it'll equal,
And it'll equal like what we do for L of x, right? So if we do L of a, it's gonna get this the same thing, which, I mean, you can sort of see it here. If this is L of x, you plug in x right here, x minus 8 minus 8 is 0. This gets canceled out, and then we're just left with whatever we plugged in for f of x originally, right?
So how would you compare how accurate d of y is?
So here's the thing. Delta y is the difference of y values when you're looking at f of x, right?
Yeah.
Dy is specifically looking at the difference of y values of the L of x, right? Of the tangent line.
So it'll give you a number that's slightly off because it's not going to keep going with the graph exactly.
Yeah. It's like the difference of them.
Yeah.
So, which you can see sort of right here. I know this is really hard and like small, but this is delta y, and it goes from this gray. It goes from this point on the gray to this other point on the gray, right? This is dy. It's smaller than it because this tangent line is below what this is, this gray is doing, right? So this dy only touches wherever you plug x into L of x. And then the difference between like this middle red part, which again, like you literally can't see, this middle red part and this part right here, that's your dy. So if I was to do it for here, I'd be looking at the difference between like right here and right here. Whereas so that would be dy, whereas delta y would be like right here to right here. And there's that difference, right?